Imagine standing at the edge of a runway as a silhouette emerges from the haze. This is not just another aircraft. This is the Boeing 787, the Dreamliner. For nearly a century, aviation was defined by the sound of roaring metal and the weight of heavy aluminum. But then, the engineers at Boeing decided to do the impossible. They decided to build a dream. Look closely at the wings as we lift off. Notice the curve, the flex. As the air pressure builds, these wings don't just hold the weight. They arc toward the heavens, like the wings of a living bird. This is the beauty of composite technology, carbon fiber woven into a masterpiece of aerodynamics. Inside the cabin, the air is different. The windows are larger. The ride is smoother. The Dreamliner didn't just change how we fly, it changed how we feel while we're in the sky. It brought the world closer by making the journey as breathtaking as the destination. Build energy slightly. From its revolutionary engines to its whisper-quiet cabin, every inch of this machine was designed to challenge the status quo. We are about to take a deep dive into the engineering, the struggle, and the ultimate triumph of this mechanical marvel. Prepare yourself, because today we're showing you exactly how the Dreamliner redefined the skies. Forever. Welcome to the future of flight.
The journey of 1,000 miles begins with a single powerful rotation. Look closely at the heart of the modern jet engine. This turbine is a masterpiece of engineering designed to harness the raw power of physics. It creates thrust, the fundamental force that overcomes inertia and pushes the massive weight of an aircraft through the resistance of the atmosphere. Without this initial surge of energy, the dream of flight would remain grounded. But once the wheels leave the tarmac, a silent, invisible tug-of-war begins. This is the dance of the four forces. Imagine the aircraft held in place by four distinct vectors of energy. Thrust drives us forward into the wind. Opposite to it is drag, the friction of the air molecules fighting against our movement. Pulling us toward the earth is weight, the relentless grasp of gravity. And finally, pointing toward the heavens, is lift. For a pilot to maintain a steady altitude, these four arrows must find a perfect, harmonious balance. But where does this incredible lift come from? The answer lies in the curvature of the wing, known as the airfoil. As we observe air moving through a wind tunnel, we see the beauty of Bernoulli's principle in action. The air moving over the top of the curved wing must travel faster than the air underneath. This speed difference creates a drop in pressure on the upper surface, effectively lifting the wing upward into the sky. Those bending lines of smoke are the visual proof of air being tamed by design. As the aircraft reaches its cruising altitude, it leaves behind a signature trail of white vapor against the blue expanse. These contrails are the final evidence of our victory over gravity. By understanding the turbine, balancing the four forces, and shaping the air itself, we have turned the sky into a highway. This is the science of flight, a perfect symphony of thrust, pressure, and human ambition that allows us to touch the edge of space.
Now that we have established the fundamental forces of flight, let's take a deep dive into how a pilot actually directs those forces using the primary flight controls, the yoke and the pedals. First, let us consider the yoke. When you are seated in the cockpit, the yoke is the primary interface directly in front of you. It is responsible for controlling two of the three critical axes of flight. When a pilot rotates the yoke to the left or to the right, it activates the ailerons. These are the hinged movable surfaces located on the outer trailing edge of each wing. By turning left, you raise the left aileron and lower the right, effectively rolling the aircraft into a controlled turn. Next, observe the results when you move the yoke forward or backward. This specific longitudinal movement controls the elevator, which is located on the tail's horizontal stabilizer. By pulling back on the yoke, you deflect the elevator upward. This force pushes the tail down and the nose up, allowing the pilot to control the aircraft's pitch. Conversely, pushing forward lowers the nose to begin a steady descent. Finally, we must look at the rudder pedals located on the floor. Unlike a car's pedals, these are not used for acceleration. Pushing the left or right pedal moves the rudder on the vertical stabilizer. This movement creates yaw, swinging the nose of the airplane left or right. In a truly coordinated turn, a professional pilot uses both the yoke and the rudder pedals in perfect harmony to ensure a smooth, stable transition through the air. By mastering these three primary inputs, roll, pitch, and yaw, the pilot maintains total command over the aircraft's trajectory. In our next section, we will see these controls in action during a high-stakes takeoff.
In the sophisticated world of modern aviation, the heart of every journey is the gas turbine engine. It is a marvel of engineering that operates on a continuous cycle of power, a cycle often simplified into 4 critical stages: suck, squeeze, bang, and blow. We begin with the first stage, suck. As the massive intake fan at the front rotates, it draws in colossal volumes of atmospheric air. While much of this air bypasses the core to provide immediate cooling and thrust, a vital portion is channeled deep into the engine's heart. This is the intake phase, where the journey begins. Next, we move to the second stage, squeeze. This air is forced into the compressor sections. Here, rows of hundreds of rapidly spinning blades pack the air molecules into a space many times smaller than their original volume. The pressure rises exponentially, and the temperature climbs, creating a highly volatile, high-pressure environment. This compression is the foundation of the engine's efficiency. Then we reach the critical third stage, bang. This is the combustion phase. The highly compressed air enters the combustion chamber, where fuel is precisely sprayed into the mix. An igniter creates a continuous, controlled explosion. The air expands violently as it reaches extreme temperatures, creating a high-energy stream of gas that roars toward the rear of the engine with incredible force. Finally, we witness the fourth stage, blow. This high-velocity gas stream passes through the turbine blades, spinning them with immense torque to power the compressor and the front fan. The remaining energy shoots out of the exhaust nozzle at supersonic speeds, creating the reactive thrust that propels a 100-ton aircraft through the sky. Suck, squeeze, bang, and blow. 4 distinct stages, working in perfect rhythmic harmony to defy gravity and conquer the skies.
Step inside the modern flight deck. You'll notice something immediately. The clutter of hundreds of mechanical dials has been replaced by sleek glass displays. This is the heart of aviation's safety revolution. Automation acts as a tireless digital co-pilot, managing the complex data streams that keep us safe in the sky. Systems like the primary flight display provide a consolidated view of altitude and airspeed, while the navigation display plots a course around weather with pinpoint accuracy. These automated tools process millions of calculations every second, detecting potential issues long before they are visible to the human eye. Safety, however, is about the synergy between human intuition and digital precision. Pilots train for thousands of hours to manage these systems, ensuring they remain the final authority in the cockpit. Even with advanced auto flight, the most critical safety feature remains the clear communication and quick decision-making of the flight crew. Automation reduces the cognitive load, allowing pilots to focus on strategic decisions during takeoff, landing, or unexpected weather changes. This layered approach, where technology monitors the physics and humans manage the mission, has made commercial aviation the safest form of travel in history. As we look forward, the flight deck continues to evolve. Enhanced vision and AI diagnostics are further narrowing the margin for error. On this deck, every pixel and command is dedicated to one goal: a safe landing. Welcome to the future of flight.
As the sun dips below the horizon, we aren't just witnessing the end of a flight. We are standing at the dawn of a new era in human movement. The roar of the past is fading, replaced by the quiet, steady hum of a sustainable future. Imagine a world where the distance between us no longer comes at a cost to the planet. We are on the precipice of a revolution, where electric propulsion and hydrogen technology transform our skies into clean corridors of connection. These are no longer just blueprints. They are the wings of tomorrow, soaring over cities that breathe easier because we chose to innovate today. Engineering has always been about the audacity to dream. From the first fabric gliders to the carbon-neutral jets of the coming decade, our journey upward has been a testament to human will. We are redefining the nature of travel, ensuring the beauty we see from 30,000 feet remains preserved for every generation waiting to take their first flight. The horizon is wide, and the path is clear. The future of flight isn't just about reaching a destination, it's about the legacy of how we get there. It is a journey of responsibility and endless possibility. So as we touch down today, keep your eyes on the clouds. The best is yet to come.